All right, hello everyone, and welcome to lesson 1.5. We're going to be talking about describing the distribution of a quantitative variable. We're still looking at univariate data and quantitative variables, and we're going to be talking about a fair amount of vocabulary we use to describe how the observations of a quantitative variable fall. Okay? Just as a reminder, where are we in terms of our work this week? We are here on Friday. I apologize for the delay due to all the internet stuff. Came back last night. I've been trying to frantically sort of get stuff up for you today so you can take care of it. I apologize, but hopefully you'll find this useful and not too bad. All right. So today we're going to be talking about distributions of a variable. And when we're talking about a distribution of a variable, the distribution of a variable tells us what values the variable takes and how often it takes those values. All right. When we talk about or describe distributions of a quantitative variable, we have to include these four things. The shape, we describe the shape. That is one of the things that is a descriptor of the distribution. The center of the variable, the variability, sometimes people call it the spread, and any outliers. Okay. And this idea of distribution, whenever you hear distribution of a quantitative variable, you need to think these things. These things should pop into your mind immediately. Shape, center, variability, and outliers. When we're talking about the shape of the distribution, we're talking about the overall structure, if any, and we'll get into that. We're talking about the center. Think of it as the quote-unquote middle of the data, where the middle of the data are. Remember, data is actually plural. The singular is datum, so the middle of the data are. That's the center. The variability or the spread, think about it as how wide the data are. How widespread are they? And then the outliers, we got to think about that as sort of observations that fall outside the overall pattern. Essentially what we do is we describe the overall pattern, shape, center, and variability, and then we describe any observations that actually don't fit that general pattern. Now, this is also today like a fairly non-mathematical approach that we're doing. The goal of this class ultimately is to actually get a lot of mathematical approaches to cinch some of this stuff down. How do we measure the center and variability of a set of quantitative data? There are ways to do that, but today we're not actually getting into the mathy stuff about it. Some people use this little acronym, statistical opinions can vary, to remember the four things they need. Statistical opinions can vary, SOCV, shape, outliers, center, variability. I like SCVO because that's actually better for the order of how you describe things. Start with the shape, then the center, then the variability, and then any outliers that you might observe in the observations. I also, since we live in Santa Clara Valley, think SCV, Santa Clara Valley, to remember the order of the first three. And then outliers are the outliers, the ones that don't fit that SCV sort of mnemonic. All right, when we describe shape, generally speaking, we use these terms. If something is sort of the right-hand side and the left-hand side of the display roughly mirror each other, we can say it is symmetric. It is also okay, things won't be perfect. So it's okay to say things are roughly symmetric, all right? Because the real world is not an organized place when it comes to data collection. We talk about things being skewed left, a negative skew, if the left side of the graph is longer than the right side. This would be a left skewed graph because the left-hand side is actually the one that is longer over here. The right-hand side sort of drops off, so this is a left skewed graph. A negative skew, you can think that the data falls longer in the negative direction. Right skewed graph, a positive skew, the data falls longer in the positive direction. The right-hand side of the graph is longer than the left-hand side, okay? Some people think about this as where's the tail of the graph? If the tail is to the left, it's left skewed. If the tail is to the right, it's right skewed. I should also remind you, I apologize. I didn't do this in this one because I've been trying to get everything together. Make sure you are setting up your notebook and getting things ready to take notes on lesson 1.5. You should be taking notes in the notebook and adding in the definitions and the details here whenever you see the little note sign or I mark that you need to do that. Sorry about that. Didn't remind you. I'm just plowing ahead. All right. Continuing to take notes. More ideas about shape. All right. We use the following terms to describe shape generally. Something is unimodal if there's one peak. Well, one peak. You see that here in this case. One peak that goes up. We talk about things being bimodal if there are two peaks. And we can describe where those peaks are, as we'll see when we get into some examples. Something is uniform if there are no prominent peaks. So keep in mind, remember, nothing is really perfect. This is a roughly uniform set of observations. You might go, well, there's a peak right here on the end, Markwalter. Yeah, well, sort of, but like if you think about the general pattern, it is relatively flat. Some people might go, well, Markwalter, isn't there a third peak up there in the bimodal graph, that little guy? Well, not really. The general shape is two peaks. So don't get too stuck on the trees. We want to look at the forest here. What is the overall picture? All right. And then something is multimodal if there's more than two peaks. So in this case, we got one peak, two peaks, three peaks. And as we'll see later on, we actually call these little things, we can think of these maybe as clusters here. And they give us three peaks. Notice that one of the peaks is actually lower than the other peaks, but that's okay. There are three distinct or prominent peaks. This idea of modal comes from the term mode, which you might recall is our measure of the most common observation. So we say something is bimodal if there's two peaks, like two areas where we have really common observations. When we're talking about the center of a set of quantitative data, we're going to use really for today one sort of term, but we'll dig into what center is and how to measure it later on. But in general, think of center, measures of central tendency, as your basic mean, median, mode thing. Median, which we'll use mostly today, is the middle observation of all observations are put in order. Roughly half the data is below, roughly half the data is above that observation, that measurement. For today, we're going to use estimates of the median, or the actual median if you can find it, when we make observations about center. So in the practice problems, if I say, find the center, just think for now median, that's what we're going to use, and either find it or estimate where that median is going to be. If you can find it, I do expect that you actually find it. Y'all did that over the summer, so you should be able to find the median. When we're talking about the variability or the spread, that actually also has some more deep sort of mathematical things involved with it. We'll talk about that stuff later, how to sort of measure variability and ways to talk about it. But think of it essentially as how wide the observations are, how widespread is it. For today, we're simply use what is the largest and smallest observations to describe the spread of the data. That's going to be sort of our easy way to do it today before we dig into more mathematical ways later. We also need to be able to describe outliers. I feel like a broken record, but we will talk more about outliers later. But in one variable data, think of them as observations that break the pattern. They're unusually small or large observations. There are mathematical ways to identify and discuss possible outliers, but for today, we're just going to kind of use our eyeballs. Today, we will simply identify observations that are way outside the general group as possible outliers. So like in this little chart right here, these are possible outliers. That's simply what we're going to say today, that in whatever this data collection was, we have these people over here. They are possible outliers. It is also worth throwing into your description of distributions, make sure you're taking notes on these things, any unusual features that arise. For example, a gap. It is worth talking about gaps in data. A gap is a region of a distribution between two data values where there are no observed data. So a gap, for example, would be right here. And gaps can be really interesting because sometimes we actually find, for example, that if we're measuring something, we find that there is actually a place where we don't see any observations. That can be really telling, and actually if we're scientists or engineers or whatever, might push us to investigate why don't we see any observations in that specific range of values. We also have clusters, which are concentrations of data, usually separated by gaps. So clusters and gaps often go together. A cluster is just a concentration of data. And those clusters can also be really important if we're collecting data. Because maybe go, well, this is weird. Why do we have a group of people or test subjects or whatever that cluster in these two areas? Maybe there's something going on that we need to investigate because these clusters are appearing. And there's some interesting clusters that have come up in data that have led to interesting sort of scientific breakthroughs and things. All right, let's do a quick example of how do we describe a distribution of data when we're looking at quantitative data. So if you're asked, hey, describe the distribution of a data set, and we're looking at a histogram or a stem and leaf plot or a dot plot or something, here's how we can do it. I like to go in order: shape, center, variability, outliers. And I work into the description any unusual features like gaps or clusters. So here is a graph here. It measures the response time of test subjects to some stimulus. The frequency is measured over here, how many people responded within each of the time things. It's hard to tell the intervals, but the intervals are actually going by 1. Each bar represents between 0 and 1 hour, between 1 hour and 2 hours, 3 hours and 4 hours, 5 hours and 6 hours. Oh, wait, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. There we go. Pull it together, Markwalter. Sorry about that. So each bar represents essentially a 1 hour interval. And here's how we can describe this distribution. The distribution of response times, notice I name specifically in here the thing that I'm measuring. The distribution of response times is bimodal. I see 2 peaks. And skewed to the right. This sort of tail off to the right, the positive skew, is what I'm noticing here. It is longer off to the right. So distribution of response times is bimodal and skewed to the right. The 2 peaks appear to be at 3 hours and 14 hours. I actually had to count up to this one, count the bars to get there, but that is at the 14-hour range up there. All right. And notice I did identify the peaks as best I can using numbers. We want to try to root things in numbers. I noticed it was bimodal, skewed to the right, and I identified the 2 peaks. There is a gap from 23 to 24 hours. Notice here, right there, we have a space. It's maybe hard to tell in the video here, but there is a little gap right there between the tail here, a gap, and there's, it looks like one observation maybe up there. That is sort of in the, we don't really have a sex here. Actually, I need to change that. That's not right. Between 22 and 23 hours. Because that first bar is 20 to 21, 21 to 22. We don't have any observations in the 22 to 23 range, and then we have 24 to 25, or 23 to 24, an observation up there. Sorry about that. There is a gap there between 22 and 23 hours. The median response, so this one I can't actually tell from here because I don't actually know what the individual observations were, but from this graph, I can kind of estimate. I have a huge peak up here at 175 frequencies, not nearly as many over here, so it looks like my median is going to be somewhere just off over this side of things. So I'm going to estimate that my median value, if I count it in, where's the middle of the observations, if I order them, it's going to be somewhere in the 6-hour range. So the median response time is roughly 6 hours. And the response times vary from close to 0 to close to 24 hours. Now notice I said close to because in a plot like this, I actually don't know what the actual observations are. I don't know what the actual observations are. So I'm just going to say close to 0 hours and close to 24 hours. That's a description of the range or the spread or variability. And then I say there is a possible outlier at 24 hours, or if I want to be more specific, near 24 hours, because I don't know what the actual observation is. So there we go. I described the shape, bimodal skewed to the right, described the peaks, just said there was a gap. Then I described the center. The median is roughly at 6 hours response time. The variability is from close to 0 to close to 24 hours. I don't know the exact. And there is a possible outlier at 24 hours. All right. So I described the SCVO in that order. I like that order. I would encourage you to do it. Notice it is also okay to say things are roughly something, since we don't actually know or have a specific way of measuring the things exactly, at least from this histogram. And I included specific numerical detail when possible. All right. I know that was a lot, but this should be in your notes. I want you to have some examples of this, and if you need to add just a quick sketch of this chart, please go ahead and do that. All right. Here's an example of other distribution descriptions. Let's say at the right here we have a back-to-back stem and leaf plot that measures that summarizes the data from observations about the number of repetitions of an activity test subjects did with or without music playing. I don't know. There's actually a lot of studies to show that music has a big impact on people and their performance and things. So maybe they're repeating. Maybe this is a measure of like test subjects and their ability to like how many jumping jacks they'll do with or without music or something like that. How many reps of jumping jacks they'll do. It's a back-to-back stem and leaf plot. So I can describe the distributions separately like this. The distribution of repetitions of the with music group is unimodal. I got one peak, and skewed to the left. Remember, stem and leaf plots, the smaller observations are at the top. So actually to the left is up in this case because we're going to smaller observations up here, going in sort of the negative direction. So it is unimodal and skewed to the left. The peak the peak is near, sorry about that, is near 125 reps. There are no gaps or clusters. The median is 124 reps. And I could actually count that. I started from 72 reps and worked my way up. I started from 149 reps and worked my way down. And the median happened to be at 124 reps. Turned out this guy right here was the median. The number of reps varies from 72 to 149 reps. There do not appear to be any outliers. So there's my description of the distribution of with music. Without music, the distribution looks bimodal. The distribution is bimodal. I got two peaks and skewed slightly to the left. Notice the skew doesn't seem to be quite as big as over here, but it's still skewed to the left. The peaks are near 79 and 118 reps. And sort of each of these ranges, 79 and sort of the 118-ish range or reps area. There are no gaps or clusters. The median is 101 reps. Again, I counted down from 122 reps down and 64 reps up and crossed stuff out until I got to the median, which happened to be 101 reps. The number of reps varies from 64 to 122. There do not appear to be any outliers. So I described each of those distributions. Go ahead and copy those down and the stem and leaf, back-to-back stem and leaf plot over here. So you have another example of how to describe distribution. All right. Oftentimes it's actually worthwhile to compare distributions. We're going to be doing that quite a lot. The best way to compare distributions is actually by discussing them simultaneously. So I actually took my descriptions of distributions on the last slide and kind of started to combine them. The distribution of repetitions with music is unimodal and skewed to the left, while the distribution of repetitions without music is bimodal and skewed slightly to the left. And you can just continue that description by sort of combining the paragraphs in each sentence or section, saying first one, then the other. So we kind of get this back and forth comparison. In this paragraph, we continue simply merging the two paragraphs on the previous slide. After we've done that, we can actually make some claims and justify them. Like we have some caveats I'll get to. So for example, I could say there seems to be a correlation between music playing and completing more reps. The median, so that's my claim, my justification is the median and range of the with music observations is greater than the median and the range of the without music observations. Actually, I want to change this slightly. Maybe saying greater than. I should say the median and range of with music observations is higher than the median and range of the without music observations, because the range actually might be bigger for with music, but the actual numbers are all slightly higher than the without music numbers there. So I could justify that claim, hey, it looks like there is a correlation between music playing and completing more reps by simply saying the median of the with music is higher than the without music observations, and the range is actually for with music is higher than the without music range. And say this possibility is worth investigating. So notice I'm not claiming that like people respond better with music. I can't actually claim that because this is just some sample and I don't know how it was taken. But it does indicate that there might be something here that's worth investigating. And that's really important. These really what we're starting to get into are what we call descriptive statistics. Descriptive statistics, or a descriptive statistic, I should say, is a summary statistic that quantitatively describes or summarizes features from a collection of information, mean, median, mode, that kind of thing. And if we're describing some collected information, we got to keep in mind that the descriptive statistics, they do not attribute properties of a data set to a larger population. Just because that data look like, oh wow, it looks like maybe that with music there's people can complete more reps. We can't actually attribute that to a larger population. We don't actually know that for sure. But it may provide us with some indication that there might be something going on. It may provide the basis for conjectures for subsequent testing. We may say, hey, it looks like there's something going on. Let's test that further and see if we can actually attribute this property to the larger population through other testing. All right? We can't extrapolate to the larger population just from descriptive statistics like this. All right, and that's where we're going to sort of wrap up today in terms of my introduction of things. This is actually a hugely important skill. We'll see it cycle back in a lot. In fact, out of all the stuff we've done so far, this is the most important lesson. You will practice this stuff by taking a short little check-in quiz. It is not graded. When I do this, this is just my way of collecting some information about how you're doing. But I am also asking that everyone, this is an adjustment from earlier this week, I'm asking that everyone actually complete at least 5 problems from the optional 1.5 homework assignment. Everyone needs to complete, at a minimum, the 5 that are listed here from page 47 of your textbook, number 65, 68, 71, 75, and 83. Everyone needs to do those, please, okay? It will be due Tuesday morning at 9 a.m. on the Google Classroom assignment that I posted, which is called Lesson 1.5 Optional Homework, but everyone should turn at least these problems in. If you do other ones, you can turn those in too. Because of the internet outage, I was also slightly delayed in getting stuff up, so answers and things will be up either today or at the beginning of the weekend, Saturday, hopefully by end of day Saturday. So I apologize for delay on all that stuff. These are really good problems. I want you to take the time with them and then check your answers against mine over the weekend and submit them to the optional homework that is already on Google Classroom. All right, take care, everyone, and always reach out to me if you have questions. Bye.